All right, the next section that we have is 16.3, which is all about conservative vector fields. So as a reminder, a conservative vector field is a vector field, capital F, let's say, and all this means is it is the gradient of some function. That's all it means to be a conservative vector field. So a little terminology before we dig into the results about conservative vector fields. We have this first term, which is the circulation. So this term is used a little bit by most of us instructors, but what you will see more often than hear this word circulation, you will see this circle here in the middle of the integral symbol. So what does this circle mean? This circle is telling us that this path C, over which we're integrating, this path is a closed path. In other words, it's some sort of loop that connects to itself. So its endpoints are the same. So you can imagine going around the loop forever. That's all it means to be a closed path. So if f is conservative, again, here's the definition of conservative, just reminding you all. And C is some path that begins at P and goes to some point Q. From P to Q in that order. Then the line integral of that vector field, of a vector field f that's conservative over this path C, well, since we know f is equal to the gradient of some other function f, we can do this replacement, and then the actual fundamental theorem for conservative vector fields says we can go ahead and evaluate the function f, the scalar potential function, at the endpoints. And this is exactly the same idea as what you have in Calc 1. In Calc 1, you have the result that the integral, so let's let capital I be the interval from A to B on the x-axis. So really, if we think of it, this I is a path. It's a straight line path in the x direction. Starts at A, ends at B. So A and B are the endpoints of I. Okay? So the integral over I of the derivative of some function f dx, the fundamental theorem of calculus says this is equal to f at your endpoints. So in this way, this result that you should all be familiar with from Calc 1 is more or less being reproduced here. The only difference is here our function f is a function of more than one variable, so that's why we're not using ddx or just dd whatever. We actually have to use the gradient because we're talking about everything, all of its variables. So you should really relate this to this. This is just a more general version of that. Okay, so if our path, so same assumptions as above, our vector field's conservative, but now we're going to assume that our path C, it is connected. It's a closed path. In this case, because the endpoints are the same, that means Q and P are actually equal. Well, if these two coordinates are equal, then we should get 0, because we're subtracting 1 from itself. Okay. So this next statement down here talks about how, under what conditions do we know or can we check that a vector field's conservative? Because sure, one way to show that a vector field's conservative is to actually find this function. And if you're able to find this f, then, well, just take the gradient of it, and if it does equal your vector field capital F, you've just shown that it is conservative. But in practice, finding this f can be difficult, and it can be a little tedious, and not every vector field is conservative. So a lot of times it's useful to check and see if your vector field is conservative before you go ahead and go through that process of finding little f. In general, you should always make sure something exists before you go looking for it. So how do we know that a vector field capital F is conservative and therefore such a potential function little f exists? Well, there's two conditions here. I just noticed in my notes here, this should be boldface. So this should be a boldface 0. It's the 0 vector. So I should correct that. So if the curl of f is the 0 vector for 3 dimensions, so this right here is for 3-dimensional vector fields, and this right here tells you for 2-dimensional fields that this difference is equal to 0. If that's true and our vector field is defined on a simply connected domain, then f is conservative, and then we know that such a function little f does exist. In my videos, and hopefully other instructors have talked about how simply connected, while it is important and we do need that to ensure that such a potential function does exist, in this class we're not going to ask you to prove that a domain is simply connected or even bother with stating that it is simply connected. I include this terminology because you do see it elsewhere, so I just wanted to include that so that the terminology, it shouldn't be unfamiliar to you. But what simply connected means is if you have a vector field on this rectangle here, this rectangle is simply connected because there's no holes in it. But if I, for instance, maybe I bore out some region here, I delete that region here, then this region here on the inside does have a hole. I can take a loop, and if I tried to shrink this loop down, I couldn't actually fully shrink it down to a single point. We need this for technical reasons. That's what simply connected means. But other than that, you don't have to do anything with it. So really, everything boils down to these two conditions. The 3D condition or the 2-dimensional condition. So if this last bullet point here talks about how this mentions one such method for finding a potential function. Essentially, if we know, so if f, capital F, the vector field, is conservative, what does this mean? Well, by definition, there exists some function f such that the gradient of this little f equals the vector field big F. So I'm going to go ahead and assume that f is a 3-dimensional vector field, in which case, i.e., let me write this out more explicitly, the gradient of a function of 3 variables equals the vector field capital F, which is also a function of 3 variables. So whatever your field is, 2-dimensional, 3-dimensional, that's how many variables your scalar potential function, little f, has. So what is the gradient of such a function? Well, let's just continue this equality. Our vector field, if our vector field has components f1, f2, f3, then our gradient here also has 3 components, the x partial, the y partial, the z partial. So then what you can do is just line up your components. Set this first component equal to this first component. So the x partial derivative of little f should equal the x component of our vector field, f1. Well, remember that the x partial derivative can be written as this. So we could integrate both sides with respect to x. Well, fundamental theorem of calculus here, this should just give us back f. So this should produce f equals the integral of the x component f1 dx. And that's exactly what we have here. And then similarly, I could have said, okay, the second component equals the second component. And if we go through all of this process, that will yield this condition. And similarly, this will yield the z condition, the third condition here, if we compare the, the third components. So this is one such way to find an antiderivative. Again, if you've been watching the videos in the that are on the YouTube channel here, or your own instructors, you probably have encountered another way to do this, which is where we differentiate, integrate, so on and so forth. As long as you're using some systematic method to find the potential function, we don't care which method you use. Yes. Okay, that is it for 16.3. There is one section remaining, 17.1. As far as chapter 16 goes, 16.3 is the last section we're covering for this exam 3. There are still two sections in chapter 16, 16.4 and 16.5, but they talk about surface integrals, which is a slightly different topic, so we reserve that for after exam 3.